of the sulfonamides. So that would be very quite some importance. Let us look at the classification of these sulfonamides. They can be classified, just as we said, of other drugs, in various ways. At times, classification can be dependent on their site of action. You can classify drugs, especially antibacterial agents, as per the site of action, as per their duration of action, and then as per their structure. So you can classify different ways, and therefore you can classify them on the basis of the site of action. We can have sulfonamides for general infection. That is those which can be used for systemic infection. So you take them and you can use them orally. This form the bulk. The bulk of the sulfonamides can be used systemically, but of course they will have differences in their profile of activity. They will have differences in their profile of biological activity, toxicity, and that for sure again is structure dependent, and you'll be able to understand it in a few minutes. So you have sulfanilamide, which we said is a prototype. You have sulfapyridine, sulfadiazine, sulfamethoxazole, sulfamethoxazole, this one sulfamethoxazine. So we do have several. There are very many. You can't even be able to know all of them, but you can get to know some of them, which you can use as examples. Some more sulfonamides for urinary tract infection. They are still systemic, but they are specific. These are for general infection. Sulfanilamide, sulfapyridine, sulfadiazine, and sulfamethoxazole. Those are some of the very common ones. But you can have some specifically for urinary tract infections. That means for urinary tract infection, it means they'll be highly water soluble. So the ones we are using for urinary infection, they should be highly water soluble. They remain in the urine and therefore are able to manage any infections within the urinary tract. So sulfonamides for urinary tract infections, still systemic, and you have sulfaisoxazole, also, and also sulfathiazole, sulfaisoxazole, and sulfathiazole. Then you have sulfonamides for intestinal infection. So for intestinal infection, it means they remain in the GIT. In other words, they are not absorbed. So for intestinal infections, either they are highly water soluble and therefore they cannot penetrate the lipid membranes and they remain in the GIT. And you have the phthalate, sulfathiazole, succinyl, sulfathiazole, and sulfasalazine. Sulfasalazine, as I said, the sulfasalazine is the one which has this amino salicylic acid, and then of course the sulfapyridine on one side. So usually when it is absorbed, it goes to a specific area where it is hydrolyzed, and that place where it is hydrolyzed, it is able to act on the colon or in the GIT to give you the activity that you want. When you can see this is succinyl, I believe you can remember the structure of succinyl: COH, CH2, CH2, COH. These are highly water soluble sulfonamide. Of course, it is a prodrug, and it will be hydrolyzed at the proper place. You see, what happens is that when you give that sulfonamide, it passes. It's not absorbed at the place where the sulfonamides are usually absorbed. It goes and it gets to a specific area where hydrolysis occurs, and since there is minimal absorption at that area, remember absorption in the GIT also is at specific area. You require to have this the hairs. You could remember what those hairs we were calling them. You need to have the features for absorption, the folds to increase the surface area. Also, the hairs to increase the surface area. Even the membrane needs to be adjusted such that it is thin enough, not very hard membrane, not very thick membrane, to allow for penetration of the drugs. So if that drug is not deposited at the area where there is maximum absorption, it can be lodged in an area where there is no maximum absorption. Therefore, minimal absorption, the drug is converted to the sulfonamide plus the amino salicylic acid, and it will act locally within the GIT, because the area where it is deposited or the area where it gets to, there is not much absorption, and of course, therefore, that's what we're seeing. So the structure allows for these drugs to have high water solubility, and they're able to move from the stomach, and they move down into the small and large intestines, and they can get to the point where they can bring specific activity. Then you have sulfonamides for local infections. When we talk about local infections, that is where you are using them topically. So sulfonamides for local infections, mainly topically, and I had already told you sulfacetamide. Sulfacetamide is used for conjunctivitis or for eye infection. Mefenamide is used again for skin infection, and silver sulfadiazine, which is used again for for the skin. Like when you have somebody who has gotten burnt, you get burns, and of course the top skin is removed. Then when you go to hospitals, and when you go there, you will find that in some of the hospitals they still apply a white paste on their eroded skin, on their burnt skin, and that white paste is what we call silver sulfadiazine. When we look at the structure of the silver sulfadiazine, you see it's slightly different from the others, because the hydrogen that we are saying is responsible for acidity has been replaced by this silver. That is why we call this drug silver sulfadiazine. When we look at the structure of mefenamide, we will see that the structure of that drug is a little bit different. It does not agree with all the SAL or sulfacetamide. Again, we did say the sulfamoyl group has been acetylated, and that again, as we have said, is used in for local infections. You'd also have those for dermatitis. This is also local infections for dermatitis, and even for leprosy, we have dapsone and solapsone. This, of course, solapsone is a derivative of dapsone. So we had mentioned this dapsone, solapsone can be used in management of leprosy, which again is a very, very specific disease. Then you have some sulfonamides which we can use in combination. Sulfonamides that we can use in combination. Remember, I'm not looking mainly at the anti-malarial agents, I'm looking antibacterial agents. So I'm mainly looking at those combinations that we use for antibacterial purposes. And we have trimethoprim and sulfamethoxazole. Sulfamethoxazole and trimethoprim. This is a very important combination. You mix trimethoprim with sulfamethoxazole, we will be able to see the role of the trimethoprim. The importance of this is mechanism based. So that combination is able to be more effective than the sulfonamide alone. And as we have said of combination therapy, it was able to prevent emergence of resistance, but it just prevents, or it slows down, it delays, but ultimately the microorganisms still find a way of developing the resistance. With computers, you must have a lot of patience. So, so we have said that is the classification as per their site of action. And of course, we have, even when we say a particular site, we have further subdivided to be very specific an exact site of action. So you can have, we have said you can have those for general infection, of course, systemic. You can have those for urinary tract. You can have those for intestinal infections. You can have those, you have said, for local infections, for even dermatitis, of course, which is also a local infection. And you can have combination therapy, where we have trimethoprim plus sulfamethoxazole. Again, I do believe pharmacology team, pharmacologists will complete that for you. Then we can classify them on the basis of their pharmacokinetic properties. In other words, we are looking at those that are poorly absorbed, those are not absorbed, those are rapidly absorbed, those are used topically, and so on. So we are looking at on the basis of their pharmacokinetic property, and mainly we are using, absorption, because absorption is also a pharmacokinetic property. And poorly absorbed sulfonamides, and of course the ones which are poorly absorbed, as we've already said, they are the ones which will be used locally. They will remain in the GIT. They will not be absorbed. They will remain in the GIT. If you have any condition in the GIT, like the inflammatory bowel disease or ulcerative colitis, then that drug can be used to manage that condition. And most of the ones which are used for ulcerative colitis or GI intestinal activity are normally the prodrugs, like you have sulfasalazine, thiazole, sulfaguanidine. You can see the guanidine moiety, a very highly soluble drug, so therefore not able to be absorbed. Salicylate, sulfapyridine, succinate, sulfathiazole. So again, you can see all these are prodrugs that will be activated within the GIT and bring about the necessary activity. But as we have said, some of them highly water soluble, like sulfaguanidine, and therefore not absorbed rapidly and rapidly excreted. So you can also have those which are rapidly absorbed, rapidly excreted, and this of course are systemic sulfonamides, and you have quite a number of them which are used locally, I think systemically, and you have sulfamethoxazole, sulfaisofxazole, sulfadiazine, sulfadimidine, sulfafurazole, sulfasomidine, sulfamethiazole, sulfacetamide, and sulfachlorpyridazine. So you have quite a number of them, and which have been used for many years. But as I have said, the use of these sulfonamides now has been restricted and really limited by drug resistance. Topically used sulfonamides, of course, the topically used sulfonamides, of course, again, sulfonamides that are not absorbed, but they are not used. See, these ones are poorly absorbed, but you are taking them orally. So that's the difference here. These are also poorly absorbed, but they are applied topically. Therefore, again, they should have minimal absorption when applied on the skin. And you have sulfacetamide, which you use for the eyes, mafenide. I was thinking that the first name you had given was wrong. Mafenide should be the correct name. Sulfathiazole and sulfadiazine. Again, as I had said, that mafenide has a slightly different structure, as we are going to see. Sulfacetamide, we have said, is acetyl. Sulfathiazole, we have already looked at. Sulfadiazine, again, as I've said, the hydrogen of the sulfamyl group, one hydrogen of the sulfamyl group has been replaced by an acetyl group, and that drug has been found to have very good local activity within the eye. Remember, when we give drugs within the eye, they're acting locally. They should have minimal absorption so that they give minimal systemic toxicity. On the basis, the final one, so we have looked at two now. We have looked at the basis of pharmacokinetic properties, and that, of course, pharmacokinetic properties also will determine the duration of action. So the next one is still a pharmacokinetic property, but we are specific on the duration of action, but it is still on pharmacokinetic properties. We have also looked on the site. So the final one is on the basis of duration of action. And as I have said, duration of action is a subset of pharmacokinetic property, because duration of action will be dependent on the rate of metabolism of that drug. And of course, metabolism is also a pharmacokinetic property. So we can actually put this as a subset of the pharmacokinetic property. So extra long-acting sulfonamides, whereby they have a very long half-life. So we have sulfasalazine, and sulfaline. These two, I don't think we'll discuss them, but sulfasalazine is one that we'll be able to discuss. Long-acting sulfonamides, sulfadoxine, which, as I had said, is an important drug in management of malaria, sulfadimethoxime, sulfamethoxypyridazine. This was also very important, again, in management of malaria, sulfamethoxydiazine, sulfafenazole, sulfamethoxine. So again, these are drugs that were of duration of activity. They are saying half-life greater than 24 hours. And indeed, like for the anti-malaria drugs, we used just to take them 3 tablets, like the sulfadoxine. You take 3 tablets once, and the other one, the sulfamethoxypyridazine, you take it only 2 tablets once, and that was enough to take care of the malaria, when, of course, the malaria was sensitive. We do have a problem now. The malaria is no longer sensitive. Intermediate acting sulfonamides, and here I'd expect the sulfamethoxazole. Sulfamethoxazole is what normally we call sulfamethoxazole plus trimethoprim is actually what you call Septrin. You'll see many prescriptions of Septrin. We'll have sulfamethoxazole plus trimethoprim. This drug is taken twice daily. That's why we are saying 10 to 24 hours. Sulfamethoxazole, sulfasomizole. Short-acting sulfonamides, half-life less than 20 hours, sulfamethiazole, and sulfaisoxazole. When, of course, the short-acting, they will also be more polar. As the drugs change in their duration of activity, do remember, we are also changing in their lipid solubility. Their lipid solubility is decreasing as they acquire a short duration of activity. They are more polar, so more readily excreted. They can't even be excreted without metabolism because they are more polar. So when you look at sulfamethiazole, sulfaisoxazole, these are drugs that have much higher water solubility. Water solubility is decreasing as you move upwards. The higher the lipid solubility, the longer the duration of activity, because for that drug to be removed from the body, it requires extensive metabolism, and extensive metabolism will take some time. For those that are already polar, some of them will just be excreted the way they are. So, of course, they will have a short duration of action, because when you give that drug, quite a lot of it will just be removed the way it is. And remember, for antibacterial activity, you must always attain the minimum inhibitory concentration. So when you give that drug and it is being excreted very rapidly, which of course also is a pharmacokinetic property, being excreted very rapidly, then it will have a short duration of action, because as it is excreted, it is not able to attain the minimum inhibitory concentration. So also, as we have said, let us understand that the duration of action also is dependent on the polarity of the drug. The more polar the drug is, the shorter the duration of action, because the more rapid the excretion. But you can still see they do not have such a short duration of action. 20 hours is not short. It means you can still be able to give these drugs either twice daily or once daily, and they will still give you good activity. So that, again, is still the classification used for treatment of systemic infections, and we are saying short-acting, intermediate-acting, long-acting, as we have already discussed. Then number 4, so those other ones, I believe you will do them in a much better way, and perhaps to greater details in pharmacology. But now the other very important classification for us in pharmachem is how we classify them as according to their structure. But that does not mean we should not know the other classification, because the other classification also is structure dependent. Apart from perhaps the site of action, the other classification, the pharmacokinetic profile, the duration, that is also structure dependent. And I have explained that the duration of action is dependent on the structure. Even the pharmacokinetic profile, sometimes absorption, again, is dependent on the structure. But we can still classify our drugs on the basis of their chemical structure. And we have number 1 is the N1 substituted sulfonamides. N1 substituted sulfonamide. So I think we need to look at that structure. This is our structure. So we are saying this is our position number 1, position number 2, position number 3, 4, 5, 6. So when we say N1 substituted sulfonamide, this is the N1 substituted. We are only saying the sulfoamyl group or the sulfanilamide group has been substituted with an R group, and we will discuss what is the influence of that R group. So N1 substituted sulfonamide, to understand that N1 substituted sulfonamides, and you can have many of them have a substitution on N1. Sulfadiazine is just an example. Sulfamethoxazole, sulfacetamide, sulfadimide. These are just examples. You can have quite many of them are substituted on N1, and with the exception of sulfanilamide. It's only sulfanilamide which is not substituted on N1. And we will find that sulfanilamide has its own challenges because of lack of substitution. So others will be substituted on N1. But when we say N1 substituted sulfonamides, we only want those ones which are substituted at N1 only. So N4 is not substituted. Then N4 substituted sulfonamides, which are usually prodrugs, and we can look at Prontosane, which was actually a prodrug. Yeah, here it is. So if you look at Prontosane, you can see your N1 is not substituted. That's why we are calling them N4 substituted. So if you look at Prontosane, which was a prodrug, N1 is not substituted, but N4, remember 1, 2, 3, 4. This 4, N4 is substituted with the amino. So it is substituted. This, in fact, is an amino group there. So if you count 1, 2, 3, 4, 1, 2, 3, 4. So it's 1, 1, 2, 4. Triamino derivative. So if you look at that, so you see that is N4 substituted. It is a prodrug. This must be cleaved because that amino group must be free if that drug is going to have activity. So N4 substituted sulfonamide example is Prontosane. Both N1 and N4 substituted sulfonamides, and we have examples where we are saying we want both the N1 and N4 to be substituted, and we have succinyl sulfathiazole, phthalate sulfathiazole. And again, let us look at those examples. I believe I have them somewhere. Yes, so here is N1 and N4 substituted sulfonamides. So we are saying both positions of the sulfonamide have been substituted. So if you look at this, you have your R1, which of course R1 is at the position of the sulfoamyl group. So you have that group at the sulfoamyl group, and at the aniline position, again, you have this group. So you can see this is succinyl sulfathiazole, and you can see this COH, CH2, C double bond O, then it is attached to the sulfonamide. So this is the succinyl sulfathiazole. So this is the group for the sulfathiazole. So this is now correct because the other one was having 2 nitrogen, I think. It's a mistake in the structure because sulfathiazole should be a nitrogen and a sulfur. So even those structures that we copy sometimes. That's why I was asked, as it was a structure I had earlier, was not a thiazole. It was a diazole. It was a thiazole. But you can see now this is a sulfur thiazole. So thiazole should only have a sulfur and a nitrogen. But the one I had earlier. So let us keep doing those corrections. So that is now succinyl sulfur thiazole. That is a thiazole ring there. And at the aniline position, you have the succinic acid. And therefore, when this drug gets in the body, it must be, this group must be. Then you have the phthalate sulfathiazole. So the sulfathiazole is still the same ring. Sulfathiazole is still maintained. Even the same structure as that one. But now at position number 4, you have the phthalate the phthalate group, and the phthalate group is this phenyl ring with 2 carboxylic acid. Of course, you see this was a carboxylic acid, but now you are forming an amide. Forming, when you combine this with the amino group, it will be an amide. The OH group will disappear, and the hydrogen on the aniline group will disappear as water, and you will have an amide bond. So this is the phthalate group. So the phthalate group is we can call it it's a phenyl dicarboxylic acid. So that's our phthalate group there, and it is the one which is joined at again position number 4 on the aniline group. That is at this position here. And of course, because it's an amino group, once you bring a carboxylic group, you will form an amide bond, and in the body, the amide bond will be cleaved, and once it's cleaved, it will give you the free amino group, and that is what you require for your drug. So again, that we are still looking at, I'm giving you the class and giving you examples. So you have both N1 and N4 substituted sulfonamides, you have succinyl, sulfathiazole, you have phthalate, sulfathiazole as examples. You could have others, but we are just examples. And miscellaneous, where you have mafenide, and if you look at a mafenide, why we are calling it miscellaneous and saying it is in a class of its own, as I said last time, the mafenide has a little bit of a strange structure. This is the sulfonyl group, but when you look at where you expect it to have an aniline, it has a methyl amino group, and that is why we are calling it miscellaneous. But it was found to have antibacterial activity, sometimes not very well understood, but it's a miscellaneous. Not really fall in the correct class. It is not correctly a sulfonamide, because sulfonamides are those drugs that have this SO2 and H2 and an NH2 at that position. Then the final one, of course, will be the silver sulfadiazine. I think I've put injectable soluble sulfur drugs, sulfafurazone, sulfadiazine, sulfamethoxazole. So even miscellaneous, perhaps you should also have had the silver sulfadiazine, because if you look at sulfadiazine, the difference between silver sulfadiazine, it has a diazine moiety, which is the pyrimidine ring. That is a pyrimidine ring for the and of course we are calling it a diazine. It's easier to remember it's silver sulfadiazine, diazine, because of the 2 nitrogens. Diazine, it represents the 2 nitrogen. This ring with, or the pyrimidine ring, is what we are calling the diazine ring. Then you can see the difference between silver sulfadiazine and the other sulfonamides. All the other have a hydrogen at this position. It is one hydrogen that is replaced by this heterocyclic ring. But in silver sulfadiazine, which is used for management of burns, it has a silver group. The hydrogen has been replaced with silver with very great retention of very selective activity, where silver sulfadiazine is actually a drug that is used for burns. So those are the main four classifications. I think four or five. Yeah, basically are four classification: N substituted, N4 substituted, N1, N4, and the miscellaneous, where we can have the mafenide and indeed also silver sulfadiazine. So we have examples all the way. So again, this is just telling us this is our general structure. Sulfanilamide is where that will be an amino group, and R will also be a hydrogen, so that is an amino group. And we are saying that's a para-amino group. That is the aromatic ring, that is the sulfanilamide group, and of course that's the N1 substitution group. So we are saying sulfanilamide, hydrogen, hydrogen, sulfacetamide, hydrogen at position number 1. So this should be this is the R here. Here, they should have put also, the R should have been here, because we are talking about this, all of them. So they have not this R. I think they left it out because all of it, or in all of them, it's a hydrogen, so they didn't bother. So we are only looking at the hydrogen. So because they should have put an R here, and this is an R1. These groups are found here. So this is this R, but because all of them have a hydrogen, then it does not really matter. They just do the amino group. So when you look at R1 there, so Sulfocetamide, this is an acetyl group, as you can see. For sulfazine, it is a pyrimidine ring there. For sulfamethoxazole, then you find that is an oxygen nitrogen. That is our sulfamethoxazole. And as I have said, sulfamethoxazole, very, very important drug. And this is the one I've said, you can still see the structure is the same. I think the one which was corrected was sulfur, one where we corrected the structure. Yeah, sulfamethoxazole, the structure is still the same. So, and the structure was corrected was the sulfathiazole. Yeah, the sulfathiazole is where the structure is actually what you expect from the name, but the sulfamethoxazole, the structure is the name, and the structure really do not agree. The structure and the name really do not agree. So this, I will not repeat again, is just structures of the drugs that we have said classified according. It's just a classification again the way we did, but now giving the structures. And we did mention that the highly soluble sulfonamides are used for urinary infections. When we look at the sulfasalazine, I had also mentioned, is hydrolyzed in the large intestine. So what happens? We said it's not absorbed in the other areas. It moves to the large intestines, and in the large intestines, it's sulfasalazine. We said it will be hydrolyzed into sulfapyridine and 5-aminosalicylic acid. And the 5-aminosalicylic acid is the one I said it's an anti-inflammatory agent, and it can be used in the management of ulcerative colitis, or what you call bowel inflammatory disease. Bowel inflammatory disease. The highly insoluble sulfonamides like sulfathiazole and succinyl sulfathiazole. The succinyl sulfathiazole has high water solubility. The one which has highly insoluble with the sulfathiazole. This are expected to have a high water solubility. So these are retained in the GIT through because of different reasons. Once a drug is highly water soluble, it will be retained. Once it is highly insoluble, it will also be retained. Because remember, for a drug to be absorbed, it must first go into solution. So it must have some good degree of solubility. For it to go into solution, go into equilibrium, and then the non-ionized is absorbed. So if a drug has very high water insolubility, it will also not be absorbed. So these two, the sulfathiazole, when we have looked at the structure, and they should be highly soluble, not insoluble. So the highly soluble sulfonamides, sulfathiazole, succinyl sulfathiazole, are retained in the lumen of the GIT tract for prolonged periods and are known as gut active. Remember, the sulfathiazole carboxylic acid, succinyl sulfathiazole also has a carboxylic acid. So I would expect them to have high water solubility. We have mentioned the topic of sulfonamides, which are mainly used. We have talked about the sulfacetamide used for ophthalmic infections. Mafenide and sulfadiazine are used on burnwood to prevent invasion by many gram-negative and gram-positive organisms. Sulfathiazole is also commonly included in wood powders for the same purpose. Remember, we did say sulfathiazole can also be used topically, so you can include it in wood powders for also as an antibacterial agent. So these we have already mentioned. So these are just the structures, and I expect you to be able to draw your own structures for these drugs. These are just the structures, so I will not go through them again. We had already mentioned all this. We have already mentioned. So now, kindly make sure you draw the structures of the various sulfonamides for each class. Each class at least know one or two, whether we are classifying them as per their pharmacokinetics, or as per their duration of action, or their site of action, or as per their structure. It will be important to be able to know one or two of the sulfonamides in each and every class. So now we can look at the structure activity relationship